video, we'll be talking about the full adder circuit. Before you go through this video, make sure that you go through my previous video on half adder circuit. Let's move on to this video. This video contains 4 sections. Number 1, what we are going to do with this video, what is the aim of this video. And number 2, what is half adder, why do we go for half adder, what is the application of half adder, what are all the theories out behind half adder circuit. Next, how to design the half adder circuit. And finally, we will be talking about the implementation of half adder circuit using logic gate simulator. So the aim is to design and implement the full adder circuit using logic gate simulator. Here we have 2 tasks. One is with the help of the half adder circuit and OR gate, how do we build the full adder circuit, and the task 2 is using the sum of product form, that is basically using the NOT and OR gate. How do we build the full adder circuit? So in this we are going to have 2 tasks. One is building the full adder using half adder, another one using the sum of product form. And let's see the theory. Before we begin the theory of full adder circuit, I just want to begin with the limitation of half adder circuit. So as you all know, the half adder is used for the purpose of adding 2 single bit numbers, and we don't have any option in adding the carry bit resulting from the addition of previous bits. So that's why we go for the full adder circuit. So let's go to the full adder circuit. So it's a combinational logic circuit where it has no memory unit. The output at any instant of time depends on the combination of the inputs, and it is used for adding 2 single bit numbers similar to half adder, but the only difference is with the carry, right? So it has the ability to perform the addition of 3 bits, right? 2 are your input, and in addition with the input you have the carry that results from the previous additions, right? So if you see here, this is a full adder block, and here you are going to have 3 binary inputs and 2 binary outputs, sum and carry. So the 2 inputs are the bits to be added, and the third input represents a carry from the previous position, right? So you have got 3 binary inputs, and here if you see 2 binary outputs, sum and carry. So again I am just giving the label for the input A, input B and C in, right? C represents carry. So since I am just using the carry as my input, so I am just giving the label C in, and my outputs are sum and the carry, right? So carry C and out is the output. So C out. So when we talk about the design, step 1, we need to understand what are all the input variables, how many that we are going to have, and how we are going to label it, right? So A, B, C are my input, all can either be 0 or 1, and here I have 2 output variables which are sum and carry, S and C out. Step 2, draw the truth table. So I have my inputs A, B, C in, and my outputs S and C out. So let's see what will happen if my inputs are 0. So I will get sum as 0 and carry as 0. And what will happen if I have a previous carry, even my inputs are 0, that is in A and B. Consider that I have the previous carry that is going to be added to the input. So I will get here the sum be 1 and carry be 0. And next possible cases, I will be just go through the cases. 0, 1, I don't have carry input. Then I will be having sum as 1 and carry as 0. And if I continue this, I will be having 1 1, so you get sum 0, carry becomes 1, you have a carry over. Then if I have 1 0 and there is no carry input, I will get 1 as sum and 0 as the carry out. Then if I have the carry input, then my sum becomes 0 and carry becomes 1. Then if I have both the inputs 1 and no carry input, I will be having sum as 0 and carry out as 1. And if I have all 1s, my sum becomes 1 and carry out becomes 1. So I have drawn the truth table. So if you look into the truth table, the inference are your S is equal to 1 when only one input is equal to 1, or when all three are equal to 1, right? This is the inference that I get. So S is equal to 1 when only one input is 1, or when all inputs are 1. And carry, if you look at the carry, out, right? I have a carry 1 whenever I have 2 or 3 inputs are equal to 1. See, here I have 3 inputs, my carry is 1. Here I have 2 inputs, my carry is 1. Here I have 2 input, my carry bit is 1. So whenever I have 2 or 3 inputs are equal to 1, I will be having a carry set. So with the help of the truth table, we are going to draw the Karnaugh map. Okay. And finally, we are going to determine the Boolean expression. So let's see for the sum S. So here is my map. So I have the input variables A, B, C, N and all my combination, right? 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay. So let's look at the sum column, right? So I am just going to fill here all 0, 0, 0, 0, 1, I have 1. Then 0, 1, 1, I have 0. Then 0, 1, 0, I have 1. Then 1, 0, 0, I have 1. Then 1, 0, 1, I have 0. Then 1, 1, 1, I have 1. Then 1, 1, 0, I have 0. Right? So this is for sum. Right? So I will just mark all ones, right, wherever it is. If I want to write the expression, let's see. For carry, I will just again form the table and I will just fill up this map with the help of my truth table, right? So whenever I have 2 or more inputs high, my carry is set, right? Accordingly, I will just fill. So this is my carry. So if I want to make the combination in finding the simplified Boolean expression, I will be having this combination. So let's see. So for sum, I am going to make use of the first form, sum of products, right? I will be writing individual expressions, right? So what is S? S is equal to first one. S is equal to A bar, B bar, C in, then A bar, B, C in, then A, B bar, C in, then I will be having A, B, C in. This is my Boolean expression using sum of product form. Then similarly for carry, I will be writing the individual bits, right? Using sum of product, I will be writing, what is this? First one, A bar, B, C in, then A, B bar, C in, then A, B, C in, then A, B, C in bar. So this is my expression for C out using sum of product form, right? Now, I am going to simplify the Boolean expression in order to perform the full adder using 2 half adder circuit and 1 OR gate. Let's see this. This is my expression that I got from sum of product form, right? So how do I simplify this? Okay, so if you see here I can take Cn bar as common, so I will be getting A bar B plus A B bar, and here if I take Cn as common, Cn A B bar plus A B, right? Again, if I want to make the simplification, see here this can be written as A bar B plus A B bar, the whole bar, right? If you simplify this, I can write this as, this remains the same, then this I can write as Cn A bar B plus A B bar, the whole bar. If you apply the break the rule, change the sign, you will get the same, right? So finally this is in the form of A bar B plus A B bar. So I will be having Cn XOR with A XOR B, right? This is my simplified Boolean expression. Now you can see this can be achieved with the help of half adder circuit. Let's see how do we accomplish this with the help of two half adder circuit and one OR gate. And similarly for carry expression, A bar B Cn plus A B bar Cn plus A B Cn plus A B Cn bar, right? So I am just taking Cn common, right? So A bar B plus B bar A, then here I am having A B, right? Cn plus Cn bar becomes 1. So finally I will be having Cn into A bar B plus A B bar plus A B. So I can write this as Cn into A XOR B plus AB. So now that we are going to have two Boolean expressions, one using sum of product, another one using half adder circuit, right? Okay, so I am just going to draw this logic diagram, or I would prefer you to give as the practice task for implementing the same full adder circuit using sum of product form what we have obtained, right, in the design process. Okay, S is equal to and this, and C out is equal to, and you are going to use NOT and OR gates for implementing these expressions. Okay, now let's see the logic diagram for implementing the full adder circuit using two half adders and one OR gate. Okay, let's see this. Okay, so how many inputs that we have? 3 inputs, A, B, C, N. Okay, so what is this? A XOR B. So what I will do? I will just make use of XOR gate. I will get here. What is the output comes from the first XOR gate? A XOR B, which is nothing but the result of a half adder sum. Okay, then what is that you have to do for adding your carry input? Again, you have to give it to the another XOR. Okay, so I will be getting X is equal to Cn XOR with A XOR B. And what is C out? So AB, right, which is nothing but the carry output of the half adder, right, AB, right. So I will be taking the input and I will use the AND gate, which yields the result of the half adder carry. Okay, then I am having A XOR B, that is the output from the first half adder. Then I am just taking this as my input to the second half adder. Then another input is Cn, right, that I will pass it to the AND gate. Finally, I will add both using OR gate. So I will get C out is equal to Cn into A XOR B plus AB. If you look into this diagram, right, how do you say that we are using two half adder circuit? If you closely observe the logic diagram, you could see. Let's see. See, what is this? This will give the sum and this will give the carry. So I consider this as the first half adder. Okay, and the next half adder second is this, right? So this will give the sum and this will provide you the carry. Okay, so here we have two half adder, first half adder and the second half adder. So that's why we are implementing the full adder circuit using two half adders to accomplish these Boolean expressions. S is equal to C in XOR with A XOR B, and C out is equal to C in into A XOR B plus AB. Okay. Next, we are going to implement this design using logic gate simulator. Okay, so how would be the circuit? Here I am passing the input AB to the first half adder. Then I am passing the output of the first adder circuit as one of the inputs to the second half adder, and third input would be passed to the second half adder, and finally the sum, what I get is the sum of the full adder circuit, and then the carry, both the carry would be added together, where I will get my carry out of the full adder circuit. So let's go to the design of half adder in logic gate simulator. So as you all aware of how to use the logic gate simulator, I am just straight away go to the circuit connection. So where I have XOR okay, so I will just do copy paste. Okay, so one for the first half adder, I will just copy and paste. So I am just going to take this as the first half adder and this as the second half adder, and then I need to sum up the carry of both the adder, right? So I will be using this OR gate. Then I need to take the inputs, right? So how many inputs that we have here? We are going to have 3, right? Copy, paste. Okay, so I am having 3 inputs, right? Okay, so I will just align in this fashion, and finally I will just redo. This is A, this is B, this is C. Okay, fine. Next I will take the output. How many outputs we have? We have 2 outputs, right? So I will just name this as sum, and here we have C already, right? I am just taking this as O, right? O is the output of the full adder, carry output of the full adder circuit. So now let us just give the wire, right? Click on the terminal where you want to connect. So this is my A and this is my B input. Then I will pass the same A here, this one. Okay, the output is going to pass to the second half adder, right, from the first, and C in is going to be this. Okay, I just switch off this. Next one, I will be adding this I will just give it to this N. Okay, another one I will just give it to this N. Right? Okay, and this one I will just, what is this? This is AB, right? I will have to connect it to this. Then I will just give this to this. And what is this? This is going to be the output, and this is going to be your input. Okay, so if you closely observe this, this is going to be your first half adder, and this is the second half adder, and output of the first half adder is taken as input to the second half adder, and Cin is connected, and the result is A XOR B XOR C. And next one is the output of the carry, right, is taken as input. So I will just connect this as the output. Okay, so this is what? This is AB, and what is this? This is Cin into A XOR B, which satisfies our carry out expression. Okay, so now let us verify the truth table. I am just giving just giving 0, 1, my sum is 1. If I make carry bit 1, so when you will get carry bit on? If 2 or more inputs are high, right? So similarly I will just make this 1. So here I have sum 1 and carry is also 1. So I am just, I will not be getting any carry if my input is only one input is acting, right? So whenever I have more than 2, I will be getting the carry out. Okay, so if you verify all the combinations, you would get the result, right? Again I am repeating, if you want to make use of the waveform, you can very well visualize this, change what is happening in the output with respect to the input what you are passing. Okay, so that's it about the implementation. So I will just say this as full. Okay, so we have done with the task 1. Using half adder circuit, we implement the full adder circuit. This is going to be, as I said, this is going to be the practice exercise. You are going to design and implement the full adder circuit using sum of product form with the help of NOT, and OR gates, and verify your results using logic gate simulators. And here are your Boolean expressions for sum and carry out. I believe you enjoyed this video. Let's see in the next video. Thank you.